Okay, in this video we're going to continue our solution to the vapor power problems, looking at problem number 2. I've brought problem number 2 is shown here. What we have in this particular case is a typical vapor power plant. However, we have a minor modification. In this particular modification, what we have done is we've actually extracted some steam out at an intermediate pressure from the turbine, and we've taken that steam to a closed feed water heater, and we allow that steam to heat the feed water up to a given condition. After going through the feed water heater, that steam is condensed to its saturated liquid condition. It is then sent back through a trap to the lower pressure associated with the condenser and mixed in with the rest of the steam that has gone through the turbine fully, and then that is brought to the pump. The pump is then brings the total feed water up to the high pressure of the system through the boiler. So in this particular problem, we have both the pump and the turbine are considered to be isentropic, and so we don't have to worry about having an efficiency associated with them. What we know is that the pressure associated with state 1 is 10 megapascals. We also know that the flow rate through the entire system is 270 kilograms per second. We are told that some of the steam is taken off at 1 megapascal at state point 2 and sent to the closed feed water heater. The remainder of the steam is then allowed to expand fully down to the 6 kPa condenser pressure. And so we have 1 megapascal at state 2, and we have 6 kPa at state 3. The feed water heater operates at the 1 megapascal, and we make the assumption that whatever we extracted off of there is condensed down to the saturated liquid condition at state 7. It is then trapped from the 1 megapascal down to the 6 kilopascal through the trap itself. That then is combined with the state 3 fluid, who then form the feed water that is pumped up to the elevated pressure of 10 megapascals. In order to solve this problem and to figure out how much mass flow was actually pulled off of the turbine at state 2, we have been told that the temperature at this particular point at state 6 is 175 Celsius. Okay, upon knowing that particular condition, we can then utilize the device panel, to then calculate the unknown mass flow rates. And so the energy balance on enthalpy for the closed feed water heater then is going to allow us to determine the mass flow rate at state 2. And that mass flow rate at state 2 then will then come around, go back into the condenser along with what's remaining at state 3 to form state 4, which is the full 270 kilograms per second. Okay, so with this in mind, we can now go to our test software, and we can go to our test apps. Okay, this is a steady flowing system, vapor power system. It is employing steam as our working fluid. And so we could then just begin the process of going through the various states. This particular problem does not ask anything about exergy, so we do not have to specify a dead state. What we do know coming in, we do know the pressure here is 10 megapascals. 10 megapascals. And we know that at that particular point, the temperature is 500 Celsius. So it's a highly elevated enthalpy associated with the steam coming through, and we do know that the m dot is equal to 270. So we have the mass flow rate, and we have the pressure and the temperature, and all of the states are identified as very much in the superheated vapor condition. And so now we're ready to go on to state 2. What we know about state 2 is that the pressure at state 2 is equal to 1,000 kPa, or 1 megapascal. We know that at that particular point, the entropy is the same as the incoming entropy. Okay, so because that stage of the turbine is isentropic, but we do not know what the m dot 2 is. Okay, so we're going to leave that blank, and eventually we will allow the device panel to calculate what that m dot 2 must be. But we're going to assume that it's going to be calculated. And so now we're ready to go to state point 3. And state point 3 is after expanding fully down to the condenser pressure of 6 kPa. We know that the entropy is also equal to the original entropy as it isentropically went from state 1 through state 2 all the way to state 3. What do we know about the m dot at that particular point is that the m dot is equal to the original m dot minus the m dot that was taken off at state 2. And so the m dot 3 is not known until we calculate the value of m dot 2, but we can still put that in equation form. We see that it's white, indicating that it's not been calculated yet. We then can go through the identify state 4. State 4 is at the pressure of the condenser, which is 6 kPa. We can go ahead and just call that P3, since P3 is the 6 kPa. What we know about m dot 4 is that all of the mass has been rejoined together, and so we do know that the m dot at 4 going into the pump is equal to the 270, which is the m dot 1. We know that the state of the condensed fluid is assumed to be equal to 0, saturated liquid coming out of the condenser. And so that's our state 4. We are now able to go to state 5, and we know that the output of the pump is to bring the pressure up to the original pressure going into the turbine, which is P1, or 10 megapascals. We also know that the pump is isentropic, and so it goes from state 4 to state 5 in an isentropic fashion. And we know that the m dot is equal to m dot 4. And so we have the conditions associated with the entrance into the closed feed water heater. As that feed water passes through the feed water heater, getting to state 6, the pressure stays the same. And so the pressure stays the same at pressure 5. And what happens is we are told that the temperature is 175 at that outlet condition. And so it still is a subcooled liquid, and we know the temperature. So it's important that we know these two thermodynamic properties, because this then gives us the value of enthalpy coming out of that closed feed water heater. What is the m dot 6? The m dot 6 is, again, the m dot at 1. That's the total flow rate of 270 through the system. And so we have the conditions at state 6. What do we know about state 7? State 7 is operating at the pressure P2, which is the 1 megapascal. It is the high energy steam that's been extracted out of the turbine that then is allowed to go down and condense to the saturated liquid condition. And so we know that The pressure and the quality are known, so we have all of the conditions there. We know that the m dot is that unknown m dot 2 that we're hoping that the device panel for that feed water heater will calculate for us. And so this is everything that we know about state 7. After state 7, we know that we go in through the trap as the trap takes the fluid back down to the 6 kPa, which is the pressure at 3 coming out of the turbine into the condenser. And so the trap is trapping the high pressure condensate, or from 7 through the trap. And the trap is assumed to be isenthalpic because of its small size. We know that there's no heat transfer and there's no work, and so it's an isenthalpic expansion process. And what we know about the mass flow rate is the same as the m dot at 2, which again, once we figure that out, we'll have a value for that. So we have everything we know about state 8. And so with that in mind, we have all of the conditions, all 8 of the states. And now we're ready to put everything together into our various device panels. And so let's go ahead and let's start with our various device panels. We'll start, as we always have, with the turbine. And the turbine is state 1 going to, now in this particular case, the turbine is expanding in one part from 1 to 2. And so we're going to go ahead and say that the first part of the turbine is the isentropic expansion from 10 to 1 megapascal with no heat transfer. And so that first part of the turbine, which has all of the fluid passing through it, is developing this amount of work. We then are going to assign our second device as being what is going through the rest of the turbine. Now in this particular case, going through the rest of the turbine, we have a state, well, let's see, now we have an issue here. We have to determine what state is actually the state associated with what's remaining in the turbine. And so for this particular case, before I identify that, I'm going to go back to the state panel and I'm going to assign a state 9. Okay, and what state 9 is going to be the pressure at 2, which is the 1 megapascal. And I'm going to make the assumption that at state 9, we basically have the same conditions as we would have at state 2. But what we now also know is that the mass flow rate at that particular point is equal to the mass flow rate original minus the mass flow rate at 2. So it's a reduced amount of mass flow that's at the same condition as P2 and S2. Okay, but it's we're going to call that state 9. So now we can go to the device panel and we can say that the remainder of the expansion is from 9 to 3. And since both 9 and 3 has the same mass flow rate, in this part of the turbine, it's going to develop a certain amount of work. Now, it doesn't calculate that yet because it still doesn't know what m.2 is. Okay, but eventually we will know that. And so then we're going to go to our device 3, which is going to be in device 3, we're going to call that a multi-mixing. And so it's a device, it's the condenser that has 2 inputs and a single output. And so the 2 inputs are going to be at state 3, and we're going to say at state 8, that's coming from the trap, and they form and join together to be state 4. And so this point right here, this exit right here, doesn't have anything coming out of it. And so we're just going to call, either of these two exits are going to be state 4. So I could either do this, or I could go and let it be this one. And so basically the mass flow rate at 3 combined with the mass flow rate at 8 then is the mass flow rate at state 4. So this condenser will have no work associated with it, but it will have heat transfer. And the heat transfer that will determine is once we calculate the m dot, we will then be able to determine how much heat transfer occurs in that particular heat exchanger. Okay, so now we're ready to go to the pump, and the pump now is a single flow pump going from state 4 to state 5. And again, the pump has no heat transfer, and so we'll be able to calculate a work associated with that. And since the m dots are known, you see that the work has been calculated there. We are now ready to look at the closed feed water heater. And so we're going to now specify device 5 as being a multi non-mixing heat exchanger. Now this is different than the one we just did for the condenser. In this particular case, because it's a closed feed water heater, we have the condition, we have state 2 coming in, extracted off of the turbine, going to state 7. And then we also have 5 coming in. That's from the pump going through to state 6. And state 6 is where we knew what the temperature was at that particular point. And so this is the closed feed water heater that has no work being developed as well as no heat transfer. And so this device right here is what is going to then calculate the mass flow rate that we don't know. And the mass flow rate is what is the mass flow rate at state 2. Now if we wanted to, we could add another device that is a single flow device that corresponds to the trap, and that would be from 7 to 8. And so that is just the trap. However, that has no work and it has no heat transfer. And so even though we add it here, nothing is actually going to be identified in terms of the cycle panel for that particular case. There will be some entropy that's being generated, so we're including that if we were interested in the overall irreversibility of the system. We have one last device that we need to establish, and that is the single flow device called the boiler. And the boiler is taking what's coming out of the closed feed water heater and boiling it or bringing it up to state 1, again with no work but all heat transfer. And so with this in mind, I have interrupted the previous video and I'm now recording an additional video after going through setting up all of the states and all of the device panels. I realized that I had made a crucial mistake. And so I'm going to then walk you through where that mistake was, and we'll finish up the problem itself. And so what I needed to do in this particular problem is I needed to establish, we had established a state 2, which corresponded to the intermediate pressure of the turbine. And so upon establishing that point, which was isentropic from state 1, I assumed that the mass flow rate up to that point was equal to m.1, which it is. And then what I needed to do is I needed to split the fluid at that point, and I generated a state 12 or 1-2, which had the same characteristics as the state 2, pressure 2 and enthalpy 2, and I left this m.12 unmarked. And then I established also a state 22, which was at the same pressure and enthalpy, but I then called it the mass flow rate there, m.1 minus m.12. And so now I've split the two fluids. When I then went into the various device panels, my first device panel was the first stage of turbine expansion. And so this 1 to 2 then was the full fluid going through there. And upon doing that with no heat transfer, it generated a certain amount of work. I then said the second device panel was now from state 22, which was a reduced amount of fluid flow rate, going to state 3. And state 3 was, at a flow rate of m.1 minus m.12. And so it had the same flow rate. So this was our second stage of the turbine. Now, I'm showing you the solved version, and so it has the m dot, and so it calculates the total work. In device 3, which is this is the condenser, and so the condenser is bringing in at 3, it's bringing in at 8, it's going out at 4, and so it calculates the heat transfer, again, because this is the solved version. Here is the key. This is the heat exchanger corresponding to the closed feed water heater. And so what I said coming in was state 12, which was a portion of the m.2. And then also that went through to state 7 without any mixing. Then I had state 5 coming from the pump going out at state 6, which was a defined condition. And so upon solving this with no heat transfer and work, it calculated the fraction, the amount of mass flow rate at 12. And it also then was able to calculate at 22, which was then the remainder. And then here is my device panel for my pump, isentropic pump, a little bit of work, and here is my device panel for the expansion, for the trap, the expansion valve. No work, no heat transfer, a little bit of entropy generation, and then I have my 6 to 1, which is my boiler. And so upon doing this, I was then able to solve all of the equations and get all of the heat transfers and work. And my cycle panel then summarizes everything. And so on my output, you'll see what the steam extracted amount was, but my thermal efficiency then is calculated to be about 42.4%, and that was equal to the heat transfer coming in. That is in the denominator, and then my net work, which is the combination of all of the two stages of turbine expansion added together, subtracting the pump work to give me my net work. So 300 over 708 was where we got the 42.5%. Okay, so with that, in my I/O panel, you'll see that I put in some user code to actually print out m.12 and m.22, and what you see on the output then is one was 78.8 and the other was 191, and so the combined total is 270. 270 was given in the problem as the total mass flow rate. So you see that it had to extract this amount, the 78.8, in order for that feed water heater to exchange enough heat to bring the feed water up to that designated 175 degrees Celsius prior to going into the boiler. And because the internalized heat coming off the turbine was used to heat the feed water, instead of having to bring external energy in, we were able to improve the overall thermal efficiency. And so this then completes the solution to this problem number 2. Thank you for listening.